Last week we covered a set of tasks in data preprocessing and what methods that we can use to deal with those tasks. Today we're going to talk about the rest of the tasks. We will start with dimensionality reduction. To put dimensionality reduction, we want to review the overall data reduction picture. Data reduction has two aspects. One is reduce dimensionality. The second is to reduce number of observations. In some cases, number of observations, to some application, the more is better. For other applications, when you actually have too much data, the entire process got slowed down. The computational efficiency is probably a lesser concern at this time than before. However, still, when you run those highly time-consuming algorithms such as neural network, you could easily spend days and weeks train a model. Think about you have to adjust the model parameter and the network architecture. Any run would take you weeks. Then it will make the entire task very, very inefficient to the extent that's impossible. So in some situations, numerosity reduction is still necessary. So we will talk about some of the methods. We already look at regression, histogram, clustering, and we're going to talk about sampling and the data cube aggregation. On dimensionality reduction, I think this concept is much more important than the numerosity reduction. This is because it's the dimensionality of the data has fundamental impact on system performance. We have studied wavelet transforms. Remember that some coefficients can be reduced to zero. So those coefficients will no longer contribute to the mining task. Therefore, we can also consider wavelet transform not only as a data smoothing strategy, but also as a data dimensionality reduction strategy. And the new strategies that we're going to talk about today is principal component analysis, log linear models, and feature selection. Before we actually dive into those techniques, we really want to get a very clear understanding why high dimensionality is a problem. So I mentioned the term curse of dimensionality a couple of times. High dimensionality is a curse because this problem impacts almost all algorithms. When the dimensionality increases, data become increasingly sparse in the feature space. We're going to use some examples to show this is true. When data is spread, observation is spread in a high-dimensional space, then the concept of density and distance becomes really blurry. They become less meaningful. In extremely high dimension, the distance measures is meaningless. And we're going to illustrate that idea too. We know that distance similarity measures is fundamental to machine learning, to compare things, to see how group things into classes or clusters. Distance is a basic concept. In high dimensional space, if distance cannot be used as an indicator to make decisions, then what can we do? Also, when you have high dimensional data, one strategy has been to mine different subspaces. This strategy would work to some extent because when you have extremely high dimensions, then the possible combinations of those dimensions to create subspaces will grow exponentially, therefore make the algorithms very inefficient. So I'm going to use some examples. Dimensionality reduction obviously tries to address all the problems that we have mentioned. So I want to use example first to illustrate the curse of dimensionality. So in this conceptual example, we have cats and dogs, and we want to separate cats from dogs. Obviously, we don't know their name. I mean, we don't know their species name. So we can have one feature. Take first feature, we might think of the weight of an animal. And if using one feature, we can imagine that we have heavy light dogs and light cats, and heavy dogs and heavy cats. Therefore, using this feature alone with this one-dimensional data, we cannot really separate dogs from cats. Then we decided, okay, let's add a second dimension. When we add a second dimension, let's see, I don't know, color of the fur. You can imagine that our training examples, those observations will be scattered more than before when we only have one feature space. Because now this training example is going to occupy this two-dimensional space. This is going to be the smallest value for feature 1. Here is the largest value for feature 1. And this dimension shows the range for feature 2. So we have a larger space and we have the same number of the training examples. So you can see the data becomes more sparse. When we have two features, we still cannot actually using a straight line to separate all the dogs from all the cats. So the classification task is a little bit challenging. We have to figure out a very complex function to group all the dogs and cats together. You can further adding new dimensions. The more dimensions you add, you are expanding the feature space. So now we have three-dimensional space, and we have same number of training examples. You can see our feature space are no longer heavily or densely occupied by the training examples. Certain area we have no training example. So we would have no idea the data, the training examples will not give us any clue in this segment of the feature space how the data might be distributed, how the observations might be distributed. So the data becomes more and more sparse. The reason that we want to use more features of more dimensions is because when the data is more scattered in a higher dimensional space, it's easier for us to find a line or hyperplane that can separate all the cats from dogs. So having that advantage at the same time, we also have the risk of having data too thinly spread in a multidimensional space. So this example illustrates this illustration shows that in order to occupy the same percentage of the feature space, we need a lot of more training examples when we have high dimensional feature space. So here in order to occupy 20% of the space, we probably just need one dog or one cat. Their value going to fall in this range. And here we probably when we have two-dimensional space, have these combinations that occupies this area, we will need more examples. When we move on to even higher dimensional space, we know that our data is so scattered that a lot of spots are empty. We definitely need a lot of more examples in order to make this three-dimensional feature space as densely populated using the training examples as this one, right? We need a lot of more cats and dogs to fill this box than putting them on this line. The reason we need training examples to occupy the full feature space that I already hinted earlier is we want to know how the data is distributed, training examples are distributed in the entire feature space in order to learn a robust model, so that we're not just accidentally giving this very small number of training examples. We can easily draw a line here, create a plan here to separate cats and dogs. But this is only because we have very sparse training examples. What if in the future that we see a dog right here, right? Currently, this area is not occupied. We don't have information there. So it's easy for us to create this hyperplan saying, hey, we separate this. However, this model probably works well on the training example, but it will not be robust when we have a lot of new examples. And that doesn't sound scary to you. I know it sounds pretty normal, right? When you have high dimensional space, you have sparse data, and we need more training examples, so what? The question is, when you have the dimensionality becomes extremely high, like thousands, 10,000s, then the meaning of the distance changed. So let's see, when we have two-dimensional space, when we draw a circle, so this is the center of the feature space. When we draw a circle, the circle occupies the most of the feature space. So we can see that all the training examples are actually represent the core of the feature space. They're all covered here. But when you increase the dimensionality, when you have three-dimensional space, then the center becomes that ball that in the center of this cube, right? And we know that the percentage of the space occupied by this ball is smaller proportional to the entire cube as compared to the two-dimensional space. Now we have more space that's not covered by this ball. This also implies we have more examples distributed at the corners and not the center space. And I cannot draw you a higher dimensional space picture than the three-dimensional space. So I went online to find this photo. I think that's probably, it should use your imagination. What you can see is when you have higher and higher dimensions, the ball, the center, that, you know, touch all the surfaces of your two-dimensional subspaces will become smaller and smaller relative to the entire feature space, which means all your training examples are going to be essentially located in the corners. They're all very far away from each other. When the dimensionality approach infinity, the distance, mathematically, people have proved that the distance between any training examples are the same. So you cannot really say this observation is more similar to another because their distance is closer. Every observation going to have roughly the same distance. This is the reason that high dimensionality creates problems in machine learning and data mining. We're going to, in the following weeks, when we study different learning algorithms, we will revisit this concept many times. We will talk about different strategies to split data into subspaces and clever ideas to reduce the change exponential computation to a more efficient way. But here, I think you should have a very clear understanding of why high dimensionality might make the classification problems easier, but also it could create huge problem. Okay, so we answered the question of, we showed everything that I mentioned earlier, that the curse of dimensionality is a problem. And then when this is a problem, then our strategy is try to avoid this problem by reduce the dimensionality. So the dimensionality reduction idea is to eliminate irrelevant features and reduce noise. Irrelevant features create noise. Those are the features that the computers have to process, but they don't add any useful information to help the system to reach the true model. And it can reduce the time and space required, memory space required in computation, and also it allows easy visualization. When you have a lot of data points, visualization can be very intuitive, counterintuitive, maybe is a better word. We have mentioned wavelet transforms and other techniques that we're going to talk about. Next, going to be principal component analysis, log linear model, and other techniques for feature selection. So I'm going to terminate this part of the video and start a new one.